All right, so back again for more, huh? All right, so we're going to be doing limiting reagents. Again, this is the third video, but it's very important to understand this concept, and it is a rough concept to grasp. I do understand that. So in limiting reagent problems, they're going to give you two different reactants, and they will not identify which one is the excess and which one is limiting. So they're kind of tricky that way. So in this problem, we're going to be calculating percent yield from two reactants. So this is for basically anybody interested, or for Chem 204 Gen Chem 1 class, and this is from Chapter 3. So a sample problem that I have from Mastering Chemistry, for example, is that they give us two different ingredients here, two different reactants, and they say that they get a certain amount of a product, and we need to know the percent yield. We can do this problem. So they say a 3.82 gram sample of magnesium nitride is reacted with 7.73 grams of water. They end up getting 3.60 grams of magnesium oxide. Now, does that mean that this is the theoretical yield? No, this is called the actual or experimental yield. I've heard it called the actual yield, experimental yield. This is what they got in the lab. So two people, or a person just like yourself, went and combined these two together, did the reaction, and got 3.60 grams of magnesium oxide. What's the percent yield? So how good were they? Did they spill sample? Did they lose things? So what percent yield? So let's talk about what the calculation for percent yield actually is. It is the experimental yield divided by the theoretical yield. Now you might be rolling your eyes and being upset, but theoretical yield is something you're going to have to calculate each and every time we do something like this. So the theoretical yield, and then it's times 100, and that equals percent yield. So we already have our experimental yield. That's what's given up here is 3.60. What we need to do is find the theoretical yield, and then you say, okay, Carla, that's one step. No, it's actually several. You're going to have to identify the limiting reactant and what's in excess. Oh my gosh, that's a lot. But once you learn how to do these problems, they become basically second nature. So you need to find the theoretical yield. So in order to do that, we're going to have to find the limiting reactant, right? And then and how do we choose that? We choose the one that is the smaller yield, right? This should all make sense as we're doing this. And then once you do this long part here, then you come up and you plug that number in here, divide, and then times 100. So let's go ahead and get started. So I just like to go the way that they do, and if you guys remember, I like to write the amounts underneath in the equation. So we have a 3.82 gram sample of this, so 3.82 grams of this, and we have 7.73 grams of this. I'm going to actually put an X over here because I don't know how many grams of magnesium oxide I'm expecting, right? I know I have 3.82 grams of this, 7.73 grams of this, and I need to know how much I'm expecting of this as far as theoretical yield goes. This is us finding the theoretical. I know it's kind of light, but I just wrote theoretical. So the first step is to take grams of this, turn it into moles of this, and then mole to mole, and then mole to gram. Woo! Next step, take grams of this, go to moles of this, and then mole to mole, and then mole to gram. Woo! And then you pick the lower of the two. So, very much like the other videos, I'm going to try to keep this in this shot here. But let's start with the first one, shall we? So 3.82 grams of magnesium nitride. And I need to turn that into moles of magnesium nitride. Now, if I had thought ahead, I would have a periodic table. Magnesium weighs 24 Hey Ricardo, what does magnesium weigh?
Magnesium weighs 24.31 grams.
Alright, cool. Thank you. A shout out to Ricardo. So if I need to turn this into moles, what do I need to do? I need the molar mass, right? So if magnesium weighs 24.31, we can do that. So I'm going to have 3 times 24.31 plus 2 times 14.007. This is math we're doing on the side, right, to get the molar mass of magnesium nitride. Okay. We got 100.944. So 100.944 grams of magnesium nitride will give me 1 mole of magnesium nitride. Perfect. Now that we're in moles, what can we do? Compare moles to moles. Remember, this is what we're trying to find is magnesium oxide. So 1 mole of magnesium nitride will give me 3 moles of magnesium oxide. That's the mole to mole ratio that you get from the coefficients. So 1 mole of magnesium nitride will give me 3 moles of magnesium oxide. And notice that I'm making sure to position them so that they will cancel out in the end. I put moles of magnesium nitride on the bottom so that it will cancel out with moles of magnesium nitride. And then the next step here, I need to convert moles of magnesium oxide into grams of magnesium oxide. How do I do that? You go back to the periodic table. Remember, the periodic table is in grams per mole. So 1 mole of magnesium oxide, how much does that weigh? Well, you take magnesium plus oxygen, which is 15.999. This is probably one of my messier videos, isn't it? 24.31 plus 15.999, we get 40.309 grams of magnesium oxide. So multiply all the top, divide by all the bottom, and we will definitely be needing another sheet of paper for this video. Multiply all the top, divide by all the bottom, so 3.82 times 3 times 40.309, and then divide by, and I'm putting it in parentheses, but I guess I didn't really need to do that because everything on the bottom here is just 1, 1, 1, and then the 100.944. 100.944. And parenthesis, and I get 4.57. We'll say 4.58 of magnesium oxide. So that's how many grams of magnesium oxide I can expect. You can expect this yield with the 3.82 grams of magnesium nitride. Now, that's all well and good, but how many grams of magnesium oxide can I expect from the 7.73 grams of water? So we just have to do that reaction now, or that calculation now. So it's just like what we did earlier. You start with 7.73 grams of H2O, put it over 1, and then I turn grams to moles. So it's actually 18.015 grams of water for every 1 mole of water. How did I know that? It's 1 oxygen plus 2 of the masses of hydrogen from the periodic table, right? So then I get to do, now that I'm in moles, I can compare mole to mole. Looks like I have 3 moles of water for every 3 moles of magnesium oxide. 3 moles of water for every 3 moles of magnesium oxide. And then what's my last step? is the question asking, I have to compare it in grams, don't I? So I need to convert this to grams. How do I do that? Periodic table again. We already did calculate the molar mass of magnesium oxide, didn't we? 1 magnesium plus 1 oxygen, right here. 1 mole of magnesium oxide weighs 40.309. So 40.309 grams of magnesium oxide is the same as 1 mole of magnesium oxide. Nice. So multiply by all the tops, divide by all the bottoms. 7.73 times 3 times 40.309. And then I'm going to hit the divide sign, and in parentheses, I'm going to multiply 18.015 times 3. End parenthesis, and I get, 17.296, so we'll call it 17.3 grams of magnesium oxide. Wow, that's a lot. So, we can expect this much with the 7.73 grams of water. So what's the difference? As soon as 4.58 grams of magnesium oxide is made, what's going to happen? The magnesium nitride is going to run out. So think about it, and the book really will help you out a lot in this, and your instructor can help you out a lot. It's like you may have all the eggs in the world, but if you're only limited to 1 bag of flour, you can only make so many cookies, right? So once you make a certain amount of cookies, you're going to run out of flour, even if you have 1,000,000 eggs in the world, right? So it's just like that. We are limited, it seems, by the amount of magnesium nitride that we have. Because as soon as we make 4.58 grams of magnesium oxide, what's going to happen? We're going to run out of magnesium nitride. So yeah, we could hypothetically make this much magnesium oxide with the water, but we would need much, much more magnesium nitride. So what did we just determine? We just determined that the magnesium nitride is limiting reagent. What else did we determine? We determined that the water must be is in excess, right? What else? We just determined that our theoretical yield is this our theoretical yield, or is this our theoretical yield? The lower one is your theoretical yield. What's this? Nothing. That's a pie in the sky dream, because we don't have enough magnesium nitride to make it. So this is our theoretical yield. So our theoretical yield is 4.58 grams of magnesium oxide is our theoretical yield. Now we go back in the way back machine and we go back to the very beginning. Look at this equation. Our experimental yield divided by our theoretical yield. Remember, this is our experimental. We should have gotten, so yeah, let's do that. Let's write that back. And then I'm just going to put a request, this is from the problem, that 3.60 is the experimental yield. Right? So, if everything went perfectly and we were complete robots and we didn't spill anything, which I promise you will happen in lab, or we didn't weigh anything poorly, or we didn't lose any solutions, we should have hypothetically made 4.58 grams of magnesium oxide. Well, we're not perfect, and we only got 3.60 grams. So, how do we find the theoretical or the percent yield? We put the experimental, which is 3.60, experimental or actual, divided by what we should have gotten. If everything went perfect, we should have gotten 4.58. You multiply by 100, and then that's our percent yield. So 3.60 divided by 4.58 times 100, we get 78.6. So we only got 78.6 of the product that we were expecting to get. Is that a terrible yield? 100% is always ideal, but it's not going to happen in the real world. So 78.6 is our percent yield. Alright, I hope this helps. I know it was a long video, but good luck, guys.